idea the kind you might have information. You know, the moments
Okay. Let's see. We can get going, can't we? What do you think? So where are we? So at the end of the last lecture, I just sort of mentioned these transform techniques, and I'm not going to say much more. We'll use them a bit today. You should have seen this before, lambda of theta? I don't know. But lambda prime of 0, you know, just in case.
Mean?
The mean, yeah. Yeah. So basically it's a moment generating function. You take the derivatives, you get all the moments. But that's not why we care in this class, okay? This class is not about computing moments. So this turns out to have some analytical value, and so does this. And I'll explain it today in today's lecture. So today is basically just really the foundations of limit theory. And again, I mean, I could say this over and over again. I mean, the main motivation for me is an analysis of algorithms. I want to know if my estimates converge to something, you know, something like that. And I need tools to do that. So it's 2 hours. We're going to just blast through chapter 2. You know, basically the first sections of chapter 2. And so I'm going to put a lot of the responsibility on you, you know, so I'm going to motivate this. I'll be the coach. But you've got an awesome textbook, and really just read every page carefully, you know, understand this material. It would be really boring if I just sat here and read the chapter to you. Okay, so the starting point is all these bounds, sort of these so basically, we often want to look at what's the probability that x exceeds some threshold. Of course, I mean, typically x is going to be a sequence of observations of a stochastic process of some sort. And the way all of these bounds are of the same form, you write this as the expectation of some function g of x. And what might g of x be? No, this is equality. Yeah. So you're jumping ahead to actually the bounds. But if it's an equality, there's only one possible g. What's that? Well, you're right that that's this is a complementary, well, it's almost a complementary CDF. But I mean, what's the function g, you know? So you have to graph g. what function, when I take its expectation, will I get the probability that x is greater than or equal to c? Hint, it's a simple function. It's the simplest function there is. It's an indicator function. I take c, I put a little dark dot, and draw a straight line. Well, that's 1. And I draw a little circular dot there, and right there. So it's the indicator function of being bigger than or equal to c. And then you say that's less than or equal to something, and whatever you put in there gives you what your probabilistic bound. Okay? All right. So let's do it. So here's an option for you. Hi. Take the function x divided by c. Now, is that greater or equal to g of x? Well, only if you look to the right. So you get screwed up to the left. So as long as you make sure your random variable is non-negative, then you can say it's true. And so that gives you Markov's inequality. So we always have whatever, whenever I dominate this by anything, like this. Okay, so we have this is the inequality which I've graphed here. This function here, it's obviously greater or equal to 0 there, so it's true. And if x is greater or equal to c, that's greater or equal to 1. So we have that. And so if I have a random variable which is non-negative, I never need it to be true for all omega. Basically I just need the probability of being negative to be 0. Then I have that the probability that x is greater or equal to c, which again is equal to the expectation of g of x. And the expectation has this monogenicity property. I can replace that by x over c. Okay, so there you have it. Now, so that's the mother of all bounds, and really all the other ones follow from that. So I could almost honestly say this is never applied. Because actually what you typically do is you normalize. So first of all, assume that there's a finite moment, and don't assume that x is non-negative, but change the question. So you have this is now if I take the absolute value, then I can say it's non-negative. That's less than or equal to 1 over c times the expectation of x minus m. Right? And that's still Markov's inequality, but done in a different way. You could also say that I could square both sides. All right? And that thing squared is still non-negative, right? Nothing's complex here. And I can apply Markov's inequality again. But for some reason, Chebyshev demanded he got a name for this. So that's Chebyshev's inequality. Okay, and of course, if you put a 3 there instead of a 2, you get Schon's inequality. Okay, but of course, you could do whatever you want. You could, and the thing, what's cool is that what you see is if you have higher moments. So let's do it. Let's put it down Schon's inequality. Put a line there. So if this is finite, you can see that the decay rate of this probability you're interested in. So we're still interested in this probability. All right. The decay rate goes to 0 faster and faster if you have higher and higher moments, which is quite natural. Okay. All right. All right. So these are typical things you look at. They're things that are used a lot. The favorite comes up next. That blue guy was really annoying. Want something that really hugs this, And that turns out to be, you take an exponential, and it's, see if I got that right. If I got that right, so if you take an exponential, so I look at x minus c, so when x equals c, I get e to the 0, which is 1. So I touch it there. And if x is bigger than c, and theta is positive, if theta equals 0, it's pretty boring. I'll just get 1, so we wouldn't look at that. But the thing is, for any theta non-negative, we get a bound. And we can play around with that. So this turns out to be really powerful. So what do we get? We get the expectation. Let's just go back to this guy here. All right. Okay, so you've got to be really careful with all of this. First, I can multiply both sides by a positive number. So let's stick to the case theta is greater than 0, so I can multiply both sides by theta. And then the exponential is monotone, so I can take the exponential of both sides. Oops. Okay, so exponential is monotone, so these are equivalent statements. So I haven't thrown anything away yet. And so when I do this, I've got a non-negative random variable here. So here x could have been negative, taking in negative values. Now I've got positive values. And by the way, I couldn't have done that here. I couldn't have subtracted m from both sides and taken absolute values. I would have lost something. Here it's all exact. And now I can use Markov's inequality, But Chernoff demanded credit, so we called it, somehow we called Chernoff's bound. It's really funny. I mean, Markov really should get all the credit, okay? All right. But, so this, of course, looks familiar, right? We've got here the moment generating function on top. And down here we've got this thing here. So the way you actually end up writing this is, I'm going to write this as the exponential of minus theta c minus lambda of theta. And stare at this for a minute and tell me what I mean. Okay. Yeah, there's a minus minus there, so that's e to the capital lambda, which is little lambda, so we're using a big lambda for taking a logarithm. And that's the log moment generating function. Okay, and that always gives me a happy face, because it has so much structure, and you know, just again, I mean, it's just me, but it comes up in my research every single day, and you'll see why over the next few weeks. All right, so that's true for every theta, and so now you can try to get the worst bound. We want to make this as small as possible to get the tightest bound, which means we want to take this, the maximum over here. The max might not exist, so we take the supremum. So we take the supreme over all theta, okay? And that's, by the way, called the convex dual of capital lambda. Yeah, well, sorry, that's a lambda, so I got distorted. So I'm packing in a lot of information there. Convex dual, that's the definition. Convex, well, that function is a convex function of theta. You can show that. Okay, you can compute its second derivative. You'll find out it's positive. All right, the second derivative at the origin is a variance, and you can get a similar interpretation for any theta. It turns out whenever you take a convex dual, this is just a definition. Okay, if you have a convex function, you put a minus sign in front, put a theta c there, take the sup over theta, and not necessarily positive, and you get by the definition of the convex dual. Okay. You can see for any theta, that's a linear function of c. And if you take the maximum of linear functions, you get a convex function. So it's also convex. So anyway, so we have this so we have this bound, which is Chernov's inequality, and really that is Chernov's inequality. I think I saw your eyes roll up. That's not Chernov's bound. That's Chernov's bound. And I is called the great function. In all sorts of different fields, you know, it comes up everywhere, in physics and information theory, everywhere. And it's convex, and it looks like this. You know, it might jump off to infinity. It'll be convex. It's non-negative. Why is it non-negative? I'll put it. Well, it's not negative because I could let theta sneak off to 0, and lambda of 0 is 0, and you know, 0 is 0. So if you just let theta crawl off to 0, you'll get this converging to 0. So it's not negative, but it actually always hits 0 at some magical location, which we'll investigate in a moment. And you can almost guess, but let's wait on that. Actually, it'll take some time to guess. Yeah. All right. Okay. So those are the three bounds. You've got the boring Markov inequality, but then it implies all these other inequalities. And this one is by far the most useful in theory. It requires strong assumptions, though. So remember, I said Sean's inequality says that the tails are lighter and lighter if you have more and more moments. So you have this probability of the deviation being bigger than c. It goes to 0 at a polynomial rate at a faster and faster rate if you've got more and more moments. If you've actually got an exponential moment, you know, then it decays to 0 exponentially at the tail. All right? So you need that strong condition of an exponential moment. For a while, people are disputing if that's a typical thing in nature. That debate is over, thank God. You can't, if something doesn't have an exponential moment, you can't test for that. You can't prove or disprove that hypothesis. So forget it. You know, to me, in my classroom, every random variable has an exponential moment. Every one that comes from nature. You know. All right. So. All right, so let's look at one example just to make this concrete. Just for this guy. Let's actually plot this for the case of an exponential random variable. Okay, so we've got x is a exponential random variable with parameter beta. That just means it has a density of this form. Okay, and we can easily compute the moment generating function. Okay, so I take the density multiplied by the function I want the expectation of, and I integrate. All right, and I can put these guys together. This example is meant to be easy, even for those who can't see a thing over here. I'm writing down beta e to the minus beta minus theta dt. Okay, and how do I compute this integral? Well, I know that I was told that's a density, so that integrates to 1 for any beta. And so therefore, that integral must, there's a t missing. There was a t missing. This integral here must be one over beta minus theta. Okay, and if you make theta really big, this becomes negative, which doesn't make any sense. And the point is that theta can't be big. Theta has to be less than beta for this integral to make sense. Okay, so so that's the moment generating function, and lambda of theta is its log. And so remember I promised you the log moment generating function is convex. And you see it here. Beta minus theta is a linear function of theta. You take the logarithm, that's a concave function of beta. And then a minus of a concave is a convex. So it's convex. Okay, cool. So then we can compute I of c, this convex dual. Okay. All right. And so we're taking so this was convex, put a minus sign, it's concave. You know, the thing that we're trying to maximize over theta is a concave function. You know? So I said if theta equals 0, it's 0. And then it does something funky like that, you know? And in fact, when it goes to minus infinity. Right. That's what I said. I said if if theta is bigger than beta, we're in trouble. That's infinity. Okay. So basically, we're looking for this point here. And so that's where the derivative is going to be equal to 0. So that's I mean, that's really key to the geometry that follows. But anyway, so we take derivatives. Okay. So at the optimizer, we have to have a 0 slope. The derivative of theta c is pretty easy. And then you get this lambda prime of theta star. And so that's something really important to know, recognize, is that we always have lambda prime of theta star of c is equal to c. You know, that's just something to throw into your memory banks. All right. But so where are we? So let's go back to, this is all general. Yeah, I mean, so writing down this and this and this, it's all general. We have to plug in our monster here. And if we plug that in, we only end up with the derivative of this logarithm here. The derivative of that with respect to theta disappears. So we'll just get a 1 over beta minus theta. And so, how annoying. So, so we have C as that ratio, and you also get that theta star, I don't want to do it. Somebody else tell me. I'll just look it up. I don't want to make a mistake. Theta star is beta minus C inverse, according to my notes. Which looks right to me. Take the inverse of both sides and flip things around. All right, so let's look at this. So I have to plug in theta star into this thing, and and we can go back to this for one of it. So if I'm saying that C is 1 over beta minus theta star, I can replace this 1 over beta minus theta star just by C. So the term here is just the log of beta C. And then here I have to plug in this ugly mouse. I have to replace theta by this awful thing. I'll get a beta C minus 1. Okay, so I found theta star, I plugged it into this, and that's what I get. So we can graph this again. So I said that our friend here is convex. I said a convex dual is always convex. Yes, it is, because that's a linear function of C. The log is concave, and the minus sign makes it convex. And you can plot this baby, and what do you get? So you get, as C goes to 0, that goes to 0, that's a minus 1. But log of 0 is minus infinity. With minus sign, it's plus infinity. So it's really blows up over here. And then at some magical place I said it hits 0. Can anybody figure out where that is? All right. How'd you get that? I mean, yeah, I guess, all right. Thank you. So if you plug in a 1 over beta, you get log of 1 is 0, and these guys cancel out. So what's the significance of 1 over beta for an exponential beta random variable? It's the mean. So there's actually 1 over beta is equal to the mean of x. And that's always where this thing's going to hit 0, which we should have known. We're going to come back to this. I'm not going to do it now. Anybody want to tell me why it's obvious? I didn't have to look at an exponential random variable to see that this is 0 at the mean. I wonder if I should come back to it. But maybe one of you is brave enough just to tell me why it's obvious.
Because derivative is the derivative is the largest there, that value.
Not largest, but I mean, it is. It comes right there. I mean, it's like that, but it's not largest. It's actually where theta is smallest. It's the fact that lambda prime of theta at theta equals 0 is always equal to the mean of x. Because I mean, that would be true for the moment generating function. It's also true for the log moment generating function. You know, just properties of logs. And so, you know, call that m, just for mean. Today's lecture we'll call that mean. And so you can check that when you perform this maximization, you can achieve this with theta going to 0. I had to put it creating equal to 0. I'm going to cheat. It's a supreme. I can make it a max. Okay, so from this fact here, if I take the max over theta equal to 0, instead of the sup over theta strictly positive, same thing, okay, I'll find it's achieved, namely again, that equation holds with theta star equals 0. But if you plug in theta star equals 0, you get 0 times m is 0, and lambda 0 is 0, okay? And so that's why you get 0. Yeah, so that's always going to happen. And then it's not going to be true anywhere else. You're going to get strictly positive everywhere else. And this turns out to be a very important fact. You're happy? Yeah. Okay. All right, cool.
Is it true for general, or it's only because you give an exponential?
No, look at here. There was nothing but an exponential here. Yeah, so you can show this is always true, as long as it exists. Okay. Yeah, so this is true for any random variable. Oh, Gaussians, I mean, random variables with a bounded support, you know, I mean, basically, you know, when will that exist? You need the distribution of x to have tails which decay fast enough, you know. So anything with a density that's supported in a bounded interval, no problem. Yeah. Okay, but exponentials, Gaussians, so yeah. Okay, cool. So anyways, that's what we get. And it goes off to infinity here. You're always going to see it blow up just before the random variable can't take on any values. So x can't take on negative values. That's why the rate function blows up before that. You know, and we'll see why over the next couple of weeks. It'll be really clear. Yeah, there's so much more you can say about this thing. I'll keep going. Any other questions?
What's the difference between that theta star being beta minus C inverse? And
That's for any C.
and that theta
And now I'd
star
say, what about C equals the mean? If you look at the special case where C is the mean, you're always going to get 0. That's my point. You know, we worked it out for every C. We got this formula for every C. But when you take C equals the mean, which is 1 over beta, you get 0. I'm saying that's a general fact. Yeah. Okay. All right. So these results are all applied to get limit theory, which I'm going to go over the rest of the lecture. Okay. And I'm not presenting these limit theorems because they're particularly important in applications. It's just that they're easy to understand, and they have counterparts in other fields, in other applications. So two big assumptions. I've got a sequence of random variables. First assumption is that they're mutually independent. And we haven't defined that, I guess.